Last time we talked about Docker bridge that allows containers to talk to each other within the host system. Today I'd like to show you what Docker does so that containers can reach other networks and the internet, or how external users can connect to our application running inside a container. If you want to integrate Docker with other networking tools or technologies such as load balancers, firewalls, or virtual private clouds, understanding Docker networking concept is essential for seamless integration. This knowledge is crucial for using Docker effectively in various scenarios, from development and testing to production deployments and complex container orchestration environments. My name is Philip. Let's get started. Let me explain what issue we'll face when we want to reach internet from a container. First, let's delete all firewall rules so we have a clean setup. Then, let's spawn an Alpine Linux container. When we want to reach the Google DNS server from the container, our source will be 172.17.02. That's the address of container's network interface. Because Google DNS server is not on our 172.17 network, the traffic will be sent to the default gateway. Let's double check that. I will ask how to get to Google DNS from within the container. To do that, I will issue IP route get and then provide the target IP. This command tells us how the packet will be routed. As expected, it will be sent to 172.17.01. That's the default gateway, effectively the bridge interface of the host. We know how to get from the container to the default gateway as it's on the same network. Let's see what happens next. The packet goes to our Docker host. I will ask the host how to get to Google DNS. Same story here. Google DNS is not on the host local network, so the packet will go out to the host default gateway, that's 172.27.97.2. That's our router. Please mind that Docker enables packet forwarding by default. Without this option, forwarding traffic between network interfaces is not possible. If we ask the router how to get to Google DNS, it will tell us to go via its default gateway. So far, everything seems easy. Packet just travels to the next hop and next hop until it reaches Google DNS. Not so fast. The thing is, the reply packet needs to know how to get back to the sender. I'm on the Docker host server. Let's check if it knows how to reach the container. Sure, it knows. It has a bridge interface on the same network. Let's go one hop further to the router. I will ask the router how to get to the Alpine container. Our router knows nothing about the 172.17 network. It's not on the routing table. That network is internal to the Docker host. Long story short, our traffic will be forwarded, but as soon as it leaves the Docker host, the first hop along the way won't know how to get back to our container network as it's private and visible only to the Docker host. How to solve this issue? The answer is by performing source address translation on the Docker host. Let me show you how it works. I did prepare a very basic firewall configuration. We create a new IPv4 table and call it NAT. You can name the table anything you want. I just wanted for it to be something meaningful. Tables groups your rules together. Then we define a chain and name it post routing. You can give any name to your chain. Next, we define the chain type as NAT to indicate we'll be doing address translation. Then we tap into the Linux networking stack on the post routing hook. Basically, our firewall rule will be applied after routing decisions have been made. We match packets going via ETH1 output interface name and performing source address translation with masquerade keyword. Basically, for every packet leaving via ETH1 interface, the source IP will be swapped with the ETH1 interface IP. Mind that ETH1 interface is our public interface that we use to reach other networks. Let me show you that. Please mind that NAT is disabled. I will run TCP dump on the Docker host ETH1 interface and limit it to ICMP packets only. Then I will attach to our container and try to ping Google DNS. The source address is the container IP and the target IP is Google DNS. Only the Docker host knows how to get back to the Docker container. Let me go back to the Docker host and enable NAT by loading our configuration. Let's check if the config has been loaded. I'm going back to the container and running the ping test again. Do you see the difference? The source IP is no longer from our private Docker network, but it's now set to ETH1 interface IP. When the router receives a packet from the 172.27 network, it will know how to replay back, as it's part of the same network. Thing to note is when we got a reply, the target IP was set to the address of the Docker host. How did the operating system know how to send the packet back to the container? Linux kernel has a mechanism called connection tracking, or contract for short. It allows it to keep track of state of the network connections. To demonstrate that, we'll use the contract tool that provides interface to connection tracking table. At the top, I will display live events, that's -e option, and filter events typed to source address translation, that's -n option. I will also limit the output to connection sourcing from our container. The bottom will show the connection tracking table, that's -l, and filter it by connection sourcing from our container. Now let's do a single ping from our container to Google DNS. At the top, we can see a new entry with ID 11 has been created in the connection tracking table. It's still in unreplied state. Then there's an update as we got a reply. At the bottom, there's the connection tracking table that includes the protocol, source, and destination IP addresses, connection tracking ID, and timeout that indicates how long the connection should be kept in connection tracking table before being expired. For ICMP, it's 30 seconds. When the timeout expires, the contract entry is removed. At the top, there's a destroy event and the contract entry is gone. Let me run a fresh Docker install and list the firewall table. Docker is doing exactly the same thing that we did manually. Configuring firewall to perform source address translation for packets going out via any interface except Docker 0. Just to sum up, when the container wants to access other networks that are outside of the host, the traffic first goes to the bridge interface running on the host, as it's the default gateway for the container. Then the host checks where to route the packet. In our case, it will go out via ETH1 as it points toward the host default gateway. After that, the source address is updated with the address of the outgoing interface so that next hop knows how to route the traffic back. Also, the connection is tracked in the contract table. This information will be needed to update the packet address on its way back. Then, the packet goes to the router. Router decides to send it via ETH0 to the internet. Of course, as private IPs are non-routable over the internet, the router performs yet another source address translation and replaces the source IP with its public IP. That's the IP of its outgoing interface. The reply packet has Google DNS as the source. The destination is set to the public IP address of the router. This time, the router performs an update of the destination address. It swaps it to the Docker interface IP, as that's the IP the packet arrived from originally. Then, the packet is routed back to the Docker host, where the destination IP is replaced once more, this time with the container IP. Finally, the packet with the reply reaches the container. In a single host Docker installation, connections going out to external networks are possible thanks to packet forwarding, connection tracking, and network address translation. All those are well-known Linux features. That was pretty straightforward. What if you would like to expose a service running inside our container? First, let's start an Nginx container. Our container is running. Let's list networking namespaces with the lsns command. There's our Nginx service running with PID 4439. Let's switch to that namespace with the nsenter command. -t option specifies the target PID, and -n option specifies that we want to enter a networking namespace. I will check the IP address of our container. It's 172.17.02. Let's also check the listening port of our Nginx service. It's 80. Let me exit the namespace. I'll try to reach the service from the Docker host. It works. We can reach the container via the Docker Zero bridge, as it's the part of the same network. Let's go to the client that has connectivity to the Docker host. First, I will check if the client can reach our Nginx container. I will query the routing table of the client with the IP route get command. The client knows nothing about our private 172.17 Docker network. As per the routing table, the only way to get to the Docker container network is via the default gateway. That's obviously wrong. Just to prove that it won't work, I will try to call the service from the client. No luck connecting to the Nginx container. However, we can reach the Docker host as it's on the same network. In order to expose our Nginx service to the external world, we'll again use network address translation, but this time we'll be updating destination address, so this technique is called destination NAT or DNAT for short. Let me show you how it works. First, let's clean the firewall rules on the Docker host. Here's a simple firewall configuration file. It has an IPv4 table called NAT, then a chain called pre-routing. The chain type is SNAT, as we'll be performing address translation. The rules will be applied on the pre-routing hook, as we want to manipulate the packets right after they are received by the network interface, but before they are delivered to the local socket. We match packets arriving on ETH1 interface that have destination TCP port set to 80, and for those packets we update the destination address to be our Nginx container. Before we apply that firewall rule, let's see how the connection behaves without it. I will perform traffic capture on ETH1 interface on the Docker host for traffic arriving to port 80 TCP. I will limit the capture only to the headers with the -s option. 14 bytes for Ethernet frame, 20 bytes for IP header, and 20 bytes for TCP header. Let me connect to the ETH1 Docker host from the client. We got a SYN packet from the client to our ETH1 on port 80 TCP. Because nothing is listening on that port, we did reply back with a reset. Let's load the firewall rule that performs the DNAT. I will now run the traffic capture again. Let's switch to the client and try calling the service via Docker's ETH1 interface IP. To limit the output, I will request only the header. Yes, we got a reply. The traffic got forwarded to the container. If we look at the capture on ETH1 interface, we see a connection between the client and the Docker host. Let's run the capture on the Docker 0 interface. The source is the client, but this time the destination IP is set to the container IP. The client still thinks that it's connecting to the Docker ETH1 interface, but in fact the destination IP gets updated to the Docker container. Moreover, on the reply packet, the source gets updated to ETH1 interface IP. All is tracked in the contract table. Let me show you what Docker is doing when you expose an application to the external world. I will start with a clean installation. At the top, I will run NFT monitor. This will show us what firewall rules are added or removed in real time. At the bottom, I will start an Alpine container with the docker run command. This time I'm adding a special parameter -p that stands for publish. It tells Docker to expose port 80 from the container to port 80 on the host. First parameter is port on the host, then colon, and there is port on the container. Look at it. Firewall rule that performs destination NAT has been added. Now it's possible to reach the container from the outside. Let's try that. Works. If we stop the container, the rule is removed. To sum up, by default containers do not expose any of its listening ports to the outside world. To make a service available, you need to use the publish option that in turn will create a firewall rule mapping container port to a port on the host. Firewall manipulation on the Docker host is done by the runtime, so you don't have to explicitly make any firewall changes if you want containers to reach other networks or expose a service. However, it's important to understand how it works behind the scenes for a few reasons. This will allow you to diagnose and resolve network-related issues effectively, allow you to ensure that containers are properly protected and are not exposed to security vulnerabilities or unauthorized access. It will also allow you to perform network optimization or create a custom network configuration tailored to your application requirements. Most importantly, you need to know the basics to proceed to container orchestration tools like Kubernetes, as it heavily relies on Docker networking capabilities.